Have you ever paused to truly think about the intricate dance happening inside your smartphone or your laptop right now?
It's kind of mind-boggling when you do.
Yeah, all those powerful components, the main processor, the graphics unit, memory, specialized accelerators.
Mhm.
They're all working in like perfect concert, exchanging vast amounts of data at blistering speeds.
So how do they actually talk to each other without, well, chaos breaking loose?
Exactly. It's this silent, invisible symphony of engineering. So today, our mission is to take a deep dive into the conductor of that symphony, the Advanced Extensible Interface, or AXI.
Right.
We've sifted through some pretty detailed source material to unearth the crucial role AXI plays in bringing these powerful, intricate chips to life,
Yeah.
especially in the world of FPGAs.
Yeah, FPGAs are a big part of this story.
We want to give you those aha moments,
Yeah.
showing you not just what AXI is, but really why it's such a foundational piece of modern tech.
And what's truly fascinating here, I think, is that AXI isn't just another dry technical specification. Not at all.
Yeah.
Think of it more like the invisible backbone, right? The high-speed data highway that enables these incredibly complex high-performance systems we all rely on every single day.
Okay.
So we're going to trace its surprising evolution, explore how it seamlessly integrates all these diverse components, peek behind the curtain a bit at the significant challenges designers tackle, and maybe even glance into the future trajectory of this absolutely critical technology.
Okay, let's unpack this core concept then. At its simplest, AXI is an open standard on-chip communication protocol.
Right. Open standard being key there.
And it's basically become the go-to standard for how all those different functional blocks inside modern system-on-a-chip SoCs designs and FPGAs connect and communicate.
The de facto standard, really.
Now, when you hear bus, you might think of like a traditional party line where everyone shares the same wires.
Yeah, the old way.
AXI isn't quite that. Instead, it defines a point-to-point interface between a manager, that's the one initiating the request,
An initiator, yeah.
and a subordinate, the one responding.
The target or responder.
So imagine it less like a crowded public bus and maybe more like a dedicated multi-lane, high-speed fiber optic connection, just directly linking two specific points within the chip.
That's a good analogy. And it's important to understand that AXI didn't just, spring into existence fully formed.
Right, it evolved.
If we connect this to the bigger picture, its journey really began with ARM's Advanced Microcontroller Bus Architecture, AMBA, way back in 1996.
Okay, AMBA.
That gave us early protocols like ASB and APB, simple stuff, relatively speaking. Then, in 99, AMBA-2 introduced the Advanced High Performance Bus, AHB.
AHB, right, heard of that. Bit of a performance boost.
Exactly, but as chips just kept getting more complex, clock frequencies soared.
Moore's Law in action.
Relentlessly pushing boundaries, yeah. And we started cramming more and more components onto a single piece of silicon. These traditional buses, they just became bottlenecks.
Like trying to force a fire hose through a drinking straw, you said.
Pretty much. This continuous demand for higher performance and the need to integrate all these diverse specialized components that directly led to AXI's introduction in AMBA-3 back in 2003.
Okay, so AMBA-3.
AXI's multi-channel point-to-point architecture was the elegant engineering solution. It enabled the parallel and pipelined data transfers that these incredibly complex, heterogeneous systems needed.
Heterogeneous, meaning lots of different types of blocks.
Yeah, CPUs, GPUs, custom logic, and often needing clever power management techniques like globally asynchronous, locally synchronous, or GALS.
GALS.
Where different parts of the chip can run at different speeds. AXI had to handle that complexity.
Okay, here's where it gets really interesting, because AXI isn't just one thing, right? There are different flavors.
That's right. The modern AXI standard, defined in AMBA-4 and later, it breaks down into three primary types you'll usually encounter.
Okay, what are they?
First, you have AXI-4. That's your high-performance memory-mapped interface, perfect for transferring big chunks of data in what we call burst transactions.
The express lane for heavy data traffic. Got it.
Then there's AXI-4 Lite, much simpler. It's a single transaction version typically used for things like configuring control registers.
So the slow and steady access road.
Yeah.
Less data-intensive stuff.
Exactly. And finally, AXI-4 Stream. This one's a unidirectional protocol designed purely for high-speed streaming data like video or audio.
No addresses needed. Just a pure fire hose of information.
Pretty much. It doesn't bother with addressing. And beyond that, AMBA-5 has even further extended things with features like the Coherent Hub Interface, CHI.
CHI. What's that for?
That helps keep data consistent across really complex multiprocessor systems. Think of it like an ultra-smart traffic controller for shared memory. Super important for coherency.
Wow, okay, so how do all these data transfers actually happen reliably, moment by moment?
Well, at its core, AXI is synchronous. Everything happens in lockstep with a clock signal, and it operates point to point.
Right.
Now, in really complex systems, you'll often find what's called an interconnect fabric or a crossbar.
Like a central switchboard?
Exactly. Connecting many AXI masters to many subordinates, managing traffic, ensuring everyone gets a turn. But for each individual connection, the fundamental handshake mechanism is the valid ready protocol.
Valid ready. Okay.
Imagine it like two people needing to high five. The source asserts valid when its hand is out, data's ready.
Okay.
The destination asserts ready when its hand is out, it's prepared to accept.
Got it.
The transfer completes, the high five happens when both are asserted simultaneously on the rising edge of the clock.
Simple enough.
But here's a crucial rule. Absolutely critical to prevent a complete standstill, a deadlock.
Okay.
The source cannot wait for ready before asserting valid.
Why is that?
Think about it. If person A only puts their hand out, if person B is already putting theirs out, and person B is doing the same.
They'd just stand there forever. Neither would start.
Precisely. AXI's rule means one side always initiates the offer, asserting valid first. That ensures the handshake can eventually happen, no deadlock.
That valid ready handshake, combined with separating the data channels, that seems like pure genius for managing complexity.
It really is. For memory-mapped AXI, like AXI4 and AXI4 Lite, you've got those 5 independent unidirectional channels.
And it's like 5 ways. Read address, read data.
Write address, write data, and write response. Yep, 5 separate paths.
Which allows parallel read and write operations. That's a massive boost for overall bandwidth.
Absolutely. Compare that to AXI4 Stream, which just needs that single unidirectional channel because it's just continuous one-way data flow.
Simpler needs.
Exactly. This decoupled nature, plus that synchronous handshake, it not only helps prevent single-point failures, but it also provides a formal back pressure mechanism.
Back pressure, like telling the center to hold on.
Yeah. It's how a slower component can politely signal to a faster one to pause, by deasserting ready. And it does this without causing any nasty timing headaches. It's built into the protocol.
Very elegant.
And to truly squeeze every last drop of performance out of modern hardware, AXI incorporates several advanced features that are, well, simply brilliant.
Okay, like what?
First, it's a burst-based protocol. Remember AXI4?
Yeah, the high-performance one.
Instead of sending just one piece of data per address, a master can transfer a massive block up to 256 transfers, or beats, in AXI4 with just a single address phase.
Wow. 256 chunks of data for one address request.
Right. It's like sending an entire novel in one envelope instead of mailing each word separately. Drastically improves bandwidth efficiency, slashes the overhead.
Makes sense. What else?
Second, AXI supports multiple outstanding transactions and out-of-order completions. This is vital.
Outstanding transactions, meaning you can send requests before getting answers back.
Exactly. Picture a busy waiter. They don't take one order, go to the kitchen, wait, deliver, and then take the next order. That'd be slow.
Right. They take a bunch of orders at once.
AXI masters can do the same. Issue several requests without waiting for each response. This keeps the interconnect pipeline full and effectively hides latency from slower things, like external DDR memory.
Hides the waiting time.
Yep. And each response is tagged with an ID. So even if responses come back out of order, maybe request #3 finishes before request #2, the system knows how to reassemble everything correctly using those IDs.
Clever. So order doesn't matter on the return trip as long as you know which request it belongs to.
As long as responses with the same ID are processed in order, yes, it's crucial for parallelism and deep pipelining.
Okay. And there was a third thing.
Finally, there's quality of service, or QoS.
QoS, like prioritizing.
Exactly. This feature allows designers to prioritize critical traffic, say, instructions from a CPU over less critical traffic, maybe from a big background data transfer initiated by a DMA controller.
So giving the important stuff an express lane on the data highway.
Precisely. It ensures vital operations always get through first and prevents resource starvation, where one component hogs all the bandwidth.
It's really important to emphasize, like you said, these advanced features bursts, out of order QoS,
Yep.
They're not just arbitrary bells and whistles, are they?
Not at all. They are direct, ingenious engineering responses to very real, very persistent performance bottlenecks and power constraints in modern hardware.
Designed to keep those data pipelines constantly full.
Exactly. Ensuring systems run efficiently even when facing memory latency or multiple components all fighting for the same precious resources.
And while, yes, they definitely add complexity to the design,
Oh, they do.
the protocol itself provides these elegant mechanisms, like the transaction IDs and QoS, to manage that complexity effectively. It's quite a marvel of foresight, really.
It is. It's held up remarkably well over the years.
So AXI gives us this powerful language, this standard way to communicate. But how do engineers actually go from, understanding the language to building functional chips?
Right, the practical side.
This brings us to the strategic role of IP cores, intellectual property cores.
Building blocks.
Think of these as pre-designed, pre-verified functional Lego blocks that you can basically just snap into your design.
Saves a huge amount of time and effort.
Absolutely. It dramatically reduces development time. And AXI, being that standardized communication interface, has been just instrumental in fostering this whole IP reuse model.
It's the glue in many ways.
It's like everyone agreed on the shape of the Lego studs, right? Making it easy to integrate components from different suppliers without major headaches.
Exactly. And we see this with critical AXI-based IP cores being absolutely ubiquitous now.
Like what kind of cores?
Well, for example, AXI DMA controllers, direct memory access.
Okay, DMA, what does that do?
These are essential for high bandwidth data transfers, usually between memory and peripherals, like a network card or maybe a specialized image processor.
Right, moving lots of data without bothering the main processor.
Precisely. They offload the heavy data movement work from the main CPU, which can then focus on more complex tasks. Huge performance gain.
Okay. Any others?
Then you have memory controllers. These are the gatekeepers connecting the AXI interfaces on the chip to the external memory, like your DDR RAM.
The bridge to the outside world's memory.
Essentially, yes. And the beauty of AXI standardization is that it ensures these complex, high-performance blocks can be seamlessly integrated and managed within a larger system, pretty much no matter who designed them.
That's the power of the standard.
Yeah.
So how does this integration actually happen in the real world for designers? Let's turn our attention to the actual tools, focusing on the two major players in the FPGA space. Xilinx, now part of AMD,
Right.
and Intel, formerly Altera.
Okay. So in the Xilinx AMD ecosystem, the primary tool for this kind of AXI IP integration is the Vivado IP integrator.
Vivado IP integrator.
Okay. It provides this graphical design canvas. Engineers literally drag and drop IP cores and connect their AXI interfaces visually. Click and connect.
Sounds easy.
Well, what's really powerful here is that Vivado IP Integrator automates many of the really complex, error-prone tasks that used to take days, maybe weeks, of manual HDL coding.
Like what?
Things like converting between different AXI variants, say AXI4 to AXI Lite, adapting data widths if one block is 32-bit and another is 64-bit, even setting up the address mapping automatically.
Wow, okay. That's huge.
Features like connection automation abstract away a massive amount of intricate hardware description language, the HDL.
So less Verilog or VHDL coding for the connections.
Much less for the interconnect itself. Even their high-level synthesis tools like Vitis HLS can now take C or C++ code and directly synthesize it into hardware blocks with AXI interfaces ready to go.
Synthesizing C code to hardware with AXI ports.
Yeah.
That's impressive.
It is. A classic example might be you have a processor core, maybe an ARM core, inside the FPGA. It configures an AXI DMA core using a simple AXI Lite interface, just writing to some registers.
Okay.
Then that DMA core using AXI4 moves a huge stream of data between an AXI4 memory controller talking to external RAM and, say, an AXI4 stream-based video processing block you design.
All connected visually in the tool.
Right. It looks simple on the screen, just lines connecting boxes. But the tool performs incredibly sophisticated operations behind the scenes to generate the correct hardware.
But it's not foolproof, right? The designer still needs to know what they're doing.
Oh, absolutely. While it simplifies things immensely, the designer's expertise is still crucial for those high-level architectural choices. Making sure the connections make sense, choosing the right IP, setting parameters correctly. That ensures the output is not just functional, but actually optimal for performance and resource usage.
Okay. And what about the Intel side?
On the Intel side, you have Platform Designer. Many people might remember it as QC.
QSys, yeah?
This tool, integrated into their Quartus Prime software, is the equivalent for bus design in the Intel FPGA world. It, too, abstracts away tricky details like bus width, timing, arbitration, making system creation much more intuitive.
Does it use AXI primarily?
Platform Designer primarily uses Intel's own Avalon bus for component interconnects internally. Avalon is another well-established standard.
Okay, so not AXI everywhere.
Not necessarily between all internal blocks, but importantly, Platform Designer provides robust AXI bridges. These bridges are absolutely vital for interfacing with things like the HARP processor system or HPS.
But HPS, that's Intel's embedded ARM processor on the chip, right?
Exactly. And also for features like the Accelerator Coherency Port, or ACP, which helps maintain cache coherency between the processor and FPGA logic.
So the bridges let the FPGA fabric talk AXI to the ARM core and its memory system.
Precisely. This allows modules in the FPGA fabric to access the HPS's memory and peripherals at high speeds, enabling serious task offloading and co-processing. So AXI is still critical there for that heterogeneous integration.
Got it. So what's the common thread here between Ising Zavato and Intel Platform Designer?
The common thread is that both of these powerful tools essentially generate all the necessary underlying HDL, the Verilog or VHDL code based on the designer's block diagram.
They write the code for you based on the picture.
In a sense, yes. For the interconnect and wrapper logic, this automation dramatically streamlines the design process. It saves countless hours.
But there's always a but.
But it's vital to reiterate, while these tools are incredibly intelligent, a deep understanding of the underlying AXI protocol, the Avalon protocol, and the hardware you're actually targeting is still absolutely necessary.
You can't just blindly connect boxes.
Exactly. Designers need this knowledge to make informed decisions, to choose the right IP configurations, the right clocking strategies, the right interconnect options, all the things that lead to an efficient design, not just one that happens to compile and vaguely function. The automated tools are powerful aids, but they are only as good as the high-level guidance and constraints they receive from a knowledgeable engineer.
Okay, so with all this incredible complexity and power that AXI unlocks, and these tools that help manage it, what are the hard truths? What are the really intricate challenges designers face when building these high-performance, often multi-clock systems using AXI?
Right, it's not all smooth sailing.
Let's start with something we've touched on, pipelining. Can you define that again, simply?
Sure. Think of it like an assembly line in a car factory. Instead of one person building whole car from start to finish, which would be slow,
Yeah, very slow.
you break the process down into smaller, registered stages. One person attaches the wheels, the next installs the engine, the next does the seats, and so on. Each stage happens in one clock cycle.
Okay, and the benefit?
This technique helps increase the operating frequency, the FX, and the overall throughput. By breaking down long combinational logic paths, the work done between clock cycles into smaller, faster steps, the whole assembly line can run much faster.
More cars per hour.
Exactly. More data processed per second.
And this is where those high-level synthesis or HLS tools come in again.
They become invaluable here. They're like expert factory managers. They can automatically detect opportunities to pipeline loops and functions in your C or C++ code.
Okay.
And they even allow developers to guide them with specific instructions, pragmas, like #pragma HLS pipeline, to achieve a target initiation interval or 2.
Initiation interval. The I1 is the goal.
Often, yes. And 2 of 1 means a new piece of data can enter the processing pipeline every single clock cycle. It maximizes how much work the chip can do per unit time, maximum throughput.
But there's a trade-off, right? Latency.
Right. The trade-off with pipelining is that it increases latency measured in clock cycles. A single piece of data has to pass through more stages, so it takes more cycles to get from input to output.
Okay.
However, since the clock period itself is shorter, the factory line is running faster, the total latency measured in time, like nanoseconds, often remains the same or can even significantly improve.
Okay. More steps, but each step is faster.
Precisely. And this is critical because this pipeline logic is incredibly data hungry. It needs a constant stream of input data to keep busy.
The assembly line needs parts delivered constantly.
Exactly. It requires a high throughput interconnect to constantly feed it data without stalling. And AXI, with its support for burst transfers and multiple outstanding transactions,
It's perfectly designed to serve this need.
perfectly designed, it keeps that data flowing efficiently through the pipeline.
That's a fantastic analogy. But okay, what happens when you have these super fast assembly lines, these clock domains, needing to talk to another part of the chip that's running at a completely different speed, or maybe even asynchronously?
Now we get to the really tricky part.
This brings us to a really critical and often difficult challenge in multi-clock designs. Clock domain crossing, or CDC.
The bane of many digital designers' existence.
Simply put, it occurs whenever a signal has to transfer between clock domains that are asynchronous, meaning their clock signals have no fixed or predictable phase relationship, or maybe just a relationship that's unknown to the designer.
Right. Two clocks ticking to their own independent drummers.
So what actually happens when signals cross these boundaries without proper handling? What are the risks?
You face two main, often subtle and dangerous issues. First is metastability.
Metastability. Sounds unstable.
It is. It's when a flip-flop's output, the basic memory element, gets caught in an unstable, undefined state. It's neither a clear zerup nor a clear one for a brief, unpredictable time.
Like a traffic light stuck between red and green.
Exactly. And that unstable state can propagate through the logic downstream and potentially crash the entire system. Very bad.
Okay, that sounds bad. What's the second issue?
The second is data incoherency, especially with multi-bit signals like a data bus or an address bus.
Incoherency.
Yeah.
Meaning the data gets scrambled.
Essentially, yeah. If different bits of a single data word are sampled by the receiving clock on slightly different clock edges because the clocks aren't aligned, the destination could read a completely invalid or garbled value.
Like reading 1.3.4.7 when it should be 1347.
That kind of thing, exactly. You get transient, incorrect values. And these CDC issues are notoriously hard to find with traditional simulation,
Why is that?
because they often depend on very rare, unpredictable timing variations between the clocks. They might only happen once in a billion clock cycles, making them nearly impossible to catch in simulation runs. They're intermittent nightmares.
Okay, so how do designers handle this? There must be solutions.
Oh yes, several key synchronization techniques have been developed over the years. For simple single-bit control signals, like a reset or an enable, a dual-flop synchronizer is usually the standard, simple, and effective solution. It gives the signal 2 clock cycles in the destination domain to settle down from any potential metastability.
Okay, 2 flip-flops in a row.
For multi-bit control signals, things get a bit more complex. You might use handshake protocols, similar in concept to valid ready, using explicit request and acknowledge signals. These are robust, but they can add latency and reduce throughput.
Right, more overhead.
But the most common and robust solution, especially for high-volume, multi-bit data transfers across clock domains, asynchronous FIFOs, first in, first out buffers.
Ah, FIFOs.
Yeah.
How do they work for CDC?
They use special dual-port memory that can be written to by one clock domain and read from by the other independently. The magic is often in how they manage the read and write pointers. They typically use gray code for the pointers.
Gray code.
Gray code has a special property. Only one bit changes between any 2 consecutive values. This prevents that data incoherency problem when the pointer value is read across the clock domain boundary. Even if the read happens right when the pointer is changing, you'll only ever get the old value or the new value, never some invalid intermediate state.
Clever. So it ensures safe pointer comparison.
Exactly. It makes the FIFO, full empty logic, reliable across domains. Now here's the really crucial point to connect back to AXI.
Okay.
While AXI's valid-ready handshake ensures robust data flow within a single clock domain,
Right, we covered that.
AXI itself does not solve the clock domain crossing problem between different domains.
Ah. So AXI doesn't handle CDC automatically.
No, it simply shifts the problem. When you need to connect an AXI interface in one clock domain to an AXI interface in another clock domain, you, the designer, must insert an explicit synchronization primitive between them.
Like an asynchronous FIFO.
Exactly. Usually an asynchronous AXI FIFO, often called an AXI clock converter or something similar. The designer is ultimately and completely responsible for implementing this safety mechanism correctly. AXI provides the high-speed road on either side, but you still need to build a safe bridge over the asynchronous river between them.
That's a critical clarification. AXI helps within a domain, but CDC requires explicit handling between domains.
You got it.
So given the sheer volume of these potential CDC paths in a complex modern solver, you mentioned potentially millions.
Easily millions in big designs.
And the maddeningly intermittent nature of the bugs they can cause.
Yep.
It seems clear that traditional verification methods, like just running simulations, just aren't going to cut it.
Not even close. Finding these invisible gremlins demands a much more systematic, continuous verification methodology. It has to go far beyond simple simulation.
So what does that involve?
Well, the industry has really moved to a comprehensive phased verification flow for CDC. It often starts with design setup validation, making sure clocks are defined correctly. Then structural analysis tools that automatically check if synchronizers are present on every single crossing path. Are the bridges actually there?
Okay, automated checks.
Followed by protocol verification, ensuring that the synchronization schemes used, like FIFOs or handshakes, are implemented correctly and the rules are never violated. And a final phase might look at reconvergence and metastability tolerance, analyzing more complex scenarios.
And why aren't the old methods enough? You mentioned simulation misses things.
Right. HDL simulation, as we said, often misses those rare asynchronous events that trigger CDC bugs. And static timing analysis, or STA, which checks setup and hold times, is fundamentally blind to asynchronous CDC because it assumes all paths are synchronous. It just doesn't see the problem.
So you need specialized tools and techniques.
Absolutely. This is where advanced techniques become necessary. Formal verification is one.
Formal, like mathematical proofs.
Exactly. It uses mathematical models to exhaustively prove the correctness of small critical modules, including CDC synchronizers. It can find corner cases simulation would never hit.
Powerful, but maybe only for small blocks.
Typically, yes. Then there's hybrid verification. This cleverly combines static analysis with dynamic simulation, often using something called metastability injection, or MSI.
Injecting metastability, you're deliberately trying to break it.
Sort of. You inject timing uncertainty or potential metastable behavior into the simulation model at the CDC boundaries to see if the downstream logic can tolerate it. It stress tests the design against real-world timing variations.
Trying to force those rare bugs to appear.
Exactly. And for debugging on actual hardware, the on-chip logic analyzers are invaluable. Tools like Yilink's ILA Integrated Logic Analyzer or Intel's Signal Tap.
Right, peeking inside the running chip.
They let you capture signals, including AXI interface signals, in real time on a running FPGA. So you can see the actual transactions and potentially catch faulty behavior.
Very useful.
And finally, there's AXI Verification IP, or VIP. These are pre-built, sophisticated verification components that understand the AXI protocol rules.
Like automated protocol police.
That's a great way to put it. They monitor the AXI transactions in your simulation and automatically flag any protocol violations, saving a huge amount of manual checking.
Wow, that's a huge amount of complexity to manage on the verification side alone. So, looking ahead now, what emerging trends are shaping the future of FPGA development and complex hardware design, building on all these foundational ideas like AXI and CDC handling?
Yeah, things are definitely not standing still. One significant trend is the increasing adoption of globally asynchronous, locally synchronous architectures, GALS, as we mentioned briefly before.
GALS, so islands of synchronous logic talking asynchronously.
Exactly. Imagine a city where each neighborhood manages its own traffic lights perfectly synchronously within the neighborhood, but they communicate across town using a less strict asynchronous message passing system.
Okay, what's the benefit?
This design paradigm directly addresses the huge power consumption and electromagnetic interference, or EMI, issues you get with large, fully synchronous designs running at high speed. And, importantly, GLS architectures inherently manage the CDC problem at the boundaries between these synchronous islands. The asynchronous communication channels handle it.
Interesting. So it tackles power and CDC.
Potentially, yes. Another key trend is the emergence of AI and machine learning-driven design tools.
AI designing chips.
Not quite designing them from scratch yet, but assisting in very complex tasks. AML is being used to optimize things like placement and routing, figuring out the best physical location for millions of logic gates and how to wire them up on the chip. That's an incredibly complex optimization problem.
Like solving a giant multidimensional jigsaw puzzle.
Exactly. And AI is also being explored to enhance the accuracy and efficiency of CDC verification itself, helping to find those tricky bugs faster.
Using AI to find the bugs caused by complexity.
Meta. A little bit. And finally, a huge trend is heterogeneous computing platforms.
Meaning mixing different types of processors.
Yes. We're seeing FPGAs, CPUs, GPUs, specialized AI accelerators, and even custom ASICs being tightly integrated into single systems, sometimes on the same chip, sometimes using advanced packaging techniques like chiplets.
Right, chiplets are becoming big.
And the AXI protocol, especially with those newer extensions like AMB-ACHI for coherency, is absolutely central to enabling seamless, high-bandwidth communication between all these diverse compute elements. It allows designers to build these incredibly powerful super teams of specialized chips, leveraging the unique strengths of each technology. AXI is the language they all agree to speak.
Fascinating. So, based on everything we've covered today, AXI basics, integration tools, the tough challenges like CDC, future trends, What are the most actionable expert recommendations you'd give to designers working with AXI-based FPGA systems right now? What's the distilled advice?
Okay, let's break it down. For design and architecture, number one, start with a high-level block diagram. Seriously, define your system's architecture and the role of each IP core early on. Don't just start coding. Plan first.
Plan first. Second, proactively choose the appropriate AXI protocol for each interface. Don't just use AXI4 full everywhere. Use AXI4 Lite for simple control registers, AXI4 full for high bandwidth burst transfers, AXI4 stream for streaming data. Use the right tool for the job.
Match the protocol to the need.
Exactly. And this is paramount, maybe the most important thing. Treat all clock domain crossings as a first-class design concern from day one.
Don't treat CDC as an afterthought.
Never. Don't wait for verification to find the problems, because it might be too late or too hard to fix then. Proactively design in robust synchronization techniques, asynchronous FIFOs for data buses, dual flop synchronizers for control signals. Build those safe bridges before the traffic starts flowing.
Be proactive about CDC safety. Got it. What about verification?
For verification, you absolutely need a comprehensive, coverage-driven flow. Don't rely solely on basic simulation.
Go beyond simulation. Yes. Combine techniques. Use formal methods for small critical modules like reset logic or synchronizers themselves. Complement static CDC analysis tools with a dynamic simulation using metastability injection to really stress test your CDC logic for real-world scenarios.
Use formal and MSI.
And always, always leverage the vendor-provided on-chip debugging tools like Xilinx ILA or Intel SignalTap. There's no substitute for seeing the real transactions on the actual hardware when you're debugging tough issues. It's your X-ray vision.
Use the on-chip debuggers and tooling.
Finally, on tooling, mastering the sophisticated design and verification tools from the major vendors, Vivado, Quartus, Platform Designer, their simulation and synthesis environments is non-negotiable. These tools are incredibly powerful, but they require expert-level guidance to truly shine.
Learn your tools well.
And leverage the extensive IP core libraries they provide. But crucially, take the time to understand the internal architecture and the constraints of these IP cores you're using. Don't just treat them as black boxes. Know their performance limits, their interface requirements.
Understand the IP you're using.
Exactly. This multifaceted approach emphasizing mastery across the entire ecosystem, from high-level architecture, protocol understanding, CDC awareness, verification strategy, down to vendor-specific tooling and IP knowledge that really defines modern, successful FPGA development.
That's a great summary. Wow, what an incredible journey we've taken today. Really, from understanding the foundational language of AXI
The invisible backbone.
to exploring the sophisticated tools that bring these complex chips to life and digging into the ingenious ways designers tackle really daunting challenges like clock domain crossing. It's really a testament to the sheer ingenuity and foresight in hardware design.
It really is, and it makes you wonder, doesn't it? If AXI enables this dizzying complexity we see today, and now we're starting to use AI to optimize the design of these systems, what hidden layers of intelligence are we actually embedding into our hardware? Layers we might not even fully realize are there until much later down the road.
Ooh, that is a thought to chew on indeed. Something for you, the listener, to ponder. Just think about how this invisible backbone of communication impacts virtually every piece of advanced technology you interact with. From the phone in your pocket to the supercomputers tackling grand scientific challenges.
It's everywhere.
It really is. We encourage you, if this sparked your interest, to maybe look up more on FPGAs or the AMBA standard or even CDC verification techniques to continue your own learning journey into this fascinating, often hidden world of digital design.